Hello and welcome to everyone for joining us in this, which is the latest of our webinars for 2015, discussing LimitState products with a focus on their features and applications. For those of you who haven't attended one of our webinars before, my name is Tom Pritchard and I'm the host for today's session. I'll be introducing you to our first speaker shortly and presenting the second section and wrapping up at the end. Today's webinar is titled Automated at Last Yield Line Analysis Using LimitState SLAB, and it will provide you with an overview of how you can apply our new yield line software, LimitState SLAB, to a wide range of SLAB analysis problems. The main topics for today are an overview of how the software works, which will be presented by Professor Matthew Gilbert, and practical application of LimitState SLAB to a range of SLAB analysis problems, which will be presented by myself. As ever, the webinar is due to last around an hour and will include 5 or 10 minutes at the end for questions. These can be posted via the question functionality that's present in the webinar interface that you should all have in front of you at the moment. We do try to answer as many of your questions as we can in the time available, but this isn't always possible, so we're sorry if we don't get round to yours. If you do have a technical question that I might take some time to answer, you're more than welcome to contact us outside of the webinar via info@limitstate.com, and we'll be happy to answer these in detail for you. So without further delay, I'd like to welcome you to our first speaker today. That's Professor Matthew Gilbert, who will be speaking about the methodology of automated yield line analysis, and I'll now pass you over to him.
Thanks very much, Tom, and thank you very much to all of you for joining us on this webinar. Okay, so before we get into the detail, just want to show you a slide which explains visually what we're going to be covering today. So the left-hand set of images show simple yield line patterns. These are plan views of concrete slabs with sagging and hogging yield lines, and these are the sorts of solutions that you can find in textbooks, and you can do hand calculations for these kind of problems. On the right-hand side, you can see more complex examples, and these are kind of yield line patterns which is very difficult to identify by hand. And the beauty of the automated method is that we can very quickly and easily now find these kind of yield line patterns, and hence we can apply the yield line methodology in a modern setting. So we can use it to demonstrate, for example, that an existing floor has more capacity than we thought, or we can use it in design of new buildings to potentially reduce the amount of reinforcement, etc., that we might need to place. And this is another view of the same slabs that we've just seen. After we've identified the yield line pattern, we can visualize exactly what that mechanism looks like using the animation feature. Sometimes the patterns are quite complex, so this is a real boon if you're trying to understand exactly how the slab is going to deform in that mechanism. Okay, before I get into the sort of meat of the presentation, I just want to say a few words about LimitState. Basically, it's a spin-out company from the University of Sheffield. The reason it was set up back in 2006 was to provide a vehicle for getting research out there into practice, providing engineers with powerful software, particularly for ultimate limit state analysis and design, and using techniques that weren't, I guess still aren't, widely used in the sector. So particularly we're talking about optimization techniques, in this case used to identify the critical yield line pattern. Because it's a company, it's an independent company, it can do things that universities can't or don't normally do so anyway, and that's to spend time making sure the applications are easy to use, fully supported, and also well validated. So the number of current LimitState products in the market, the first two of these are shown on screen now. So the first tool was for masonry arch bridge analysis, so using limit analysis or plastic methods to quickly identify the failure mechanism of masonry arch bridge. In the UK, large percentage of bridges on the highway and rail networks are masonry, so clearly of interest in the UK and in many countries in Europe and certain countries worldwide. Second tool was a geotechnical software tool, LimitState Geo. Wider applicability potentially, and together those tools are used in over 30 countries worldwide. Just to give you a quick flavour of the types of companies that are using the software, we've got an A to Z list on our webpage, and this slide shows A and I think the first B. So lots of big companies, ACOM, AMI, Arup, but also smaller organisations, local authorities. For example, there's a local authority at the start there, Aberdeen City Council. So it's widely used software now in the UK and in many countries worldwide. So what motivated us to develop the software in the first place? If we look at the big picture, if we consider the analysis field as a whole, what we can observe is that linear elastic analysis has made that kind of analysis very convenient and mainstream. So the elastic finite element method effectively means that it's very, very easy to analyze any shape, size of structure or construction. On the other hand, if you think about plastic analysis, these tools have remained much less well developed. So, for example, we've got a yield line analysis shown on the bottom right there, which has generally remained a hand-based technique. And what we wanted to do was to change that situation. For those of you not familiar with rigid plastic or limit analysis, generally speaking, it makes an assumption about the mode of response of the material. It says basically that you can ignore elastic deformations, and you can assume that the failure is a ductile, takes place in a ductile manner, so you have effectively a rigid plastic response as shown on the load deflection graph on the right. The major considerations as far as the engineer are concerned are when it comes to analysing the ultimate or collapse limit state. If you use elastic methods, then you can end up with conservatism, basically. Conversely, when you use plastic methods, you tend to get more economical solutions when you're considering about the design context, and in assessment you can reveal hidden reserves of strength. So let's have a look at the sort of landscape when it comes to collapse analysis in a number of different subsectors. So, for example, if we're doing a geotechnical analysis, we've generally had polarization between traditional hand calculation methods or automated hand calculation tools on the one hand, and what you might call advanced tools, which use techniques such as nonlinear finite elements on the at the other extreme. And there's basically been a big gap in between those two types of tool. And our aim has been to fill that gap with mainstream tools that use numerical rigid plastic analysis. And we can do this for geotechnical problems. We can also do this for example, masonry match bridge problems. And clearly of interest today is that we can now do this for concrete slab problems as well. Benefits are that you can potentially quickly get a solution without the need for large numbers of input parameters, long run times, lots of training, lots of in-depth expertise that's needed, for example, at the advanced end, and conversely, you're likely to be able to get much more refined solutions than you can with hand calculations. Okay, so let's spend a few minutes just looking at the yield line method. It seems that the term yield line was coined back in the 1920s by Ingerslev, and actually there's a paper that appears in the Structural Engineer in 1922 on the strength of rectangular slab, which seems to be the first paper to mention the term yield line. But Johansson, some years later, really developed the method as we now know it, and it was subsequently shown that Johansson's yield line method is actually an upper bound plastic analysis method. So in other words, it's a mechanism method of analysis. How does it work in terms of the calculations? Various different approaches you can take. Probably the most common is the work method, where we equate internal and external work for a chosen yield line pattern. So in other words, we choose a yield line pattern, we do the calculations, and then we might, depending on the particular problem, try one or more other yield line patterns to check that we've actually found the critical one. If we don't find a critical one, then we end up with an upper bound solution, i.e. an unconservative indication of the true capacity of the slab. So what are the pros and cons of the yield line method? Pros is it's pretty simple. Calculations are relatively simple. You get straight to the collapse load. You don't worry about what happens prior to collapse. From the sort of broader perspective, we end up with economical designs or realistic assessments of the capacity of an existing slab. Cons are it is unsafe if you choose the wrong mechanism, and another con, I guess, is that it does only consider flexural failure, so it doesn't tell you anything about, for example, serviceability, deflections or cracking, and it doesn't, for example, consider other failure modes such as, for example, shear failure. In terms of interest in the method, it certainly was popular in the 60s and 70s. There appeared to be renewed interest in the 90s and 2000s. For example, when it comes to assessment, Middleton and co-workers at the University of Cambridge showed that many existing concrete bridges appeared to have a lot more strength than traditional calculations were indicating. So we've got a bar chart here which shows 21 structures. The red bar indicates the assessed capacity using elastic methods. The green bar indicates the yield line or plastic assessment value, and you can see there's a huge increase in the predicted capacity for many of these bridges. How were the calculations done? Well, actually, a large number of postulated failure mechanisms were programmed into software. Here we've got a list of 27 mechanisms, and each one of those mechanisms would be checked for each bridge that was analysed. So, large number of mechanisms. However, there's always a concern that there are more mechanisms that could take place or could be critical that aren't considered in the software. So there's a slight danger that the prediction is actually slightly non-conservative. Similar time, there was interest from the design side as well. So a large scale building model was constructed in the airship hangar at Cardington, and one of the objectives was to evaluate different methods of designing concrete slabs, either using elastic methods or using yield line methods. And what they found was that when yield line design was used, they ended up with relatively low amounts of reinforcement in terms of weight. So we've actually got 14.5 tons as opposed to, at the other extreme, 25.5 tons with fine element design methods. And also, the second column indicates that we end up with relatively simple reinforcement layouts. We've actually got less bar marks than many of the other techniques. So low steel tonnage, simpler layouts equate to very economical design solution. So at the time, a guidance document was produced by the Concrete Centre in the UK, Practical Yield Line Design by Kennedy and Goodchild. The foreword says yield line design is easy, which sounds wonderful, but there is a caveat once you know what you're doing. And the big problem is that an insufficient number of engineers had the confidence to use the techniques described in that design guide, and so yield line design is actually, in practice, certainly in the UK, much less well used now than elastic design. So, how did we manage to automate the yield line method? Actually, before I get into that, I'm just going to just quickly give you a taste for how we've done it in terms of software, and then hopefully it will be of more interest to look at the details. So what I'm going to do is I'm going to just show you how quick and easy it is to set up a regular slab geometry and solve that and view the yield line pattern. So in the software, which Tom Pritchard is going to talk you through in much more detail later on, what I'm going to do is I'm going to choose an empty project. So I'm going to click Finish, and what I have is effectively a blank canvas. At the left-hand side, I have some drawing tools. So, for example, I can use the drawing tools to, for example, specify the geometry of a slab, and I'll choose a somewhat unusual shape just to show that you can do that. So I've now got a slab. I'll turn off the grid lines. I can select the different areas of the slab. So, for example, the boundaries I can select, and I can, for example, choose, say, simple supports. So I now have a slab geometry, some supports. What I now need to do is apply a material. I'm just going to apply a unit MP, so it's the benchmark material to start with, and I also need to apply a load. And I'm going to apply a pressure load, and I'm going to have a benchmark unit pressure load just for simplicity. I now need to click the green button, and straight away I get a yield line pattern, and the software will animate that directly after solve. So what I'm able to do is very, very rapidly do the yield line analysis and to visualize the mechanism. So probably in the space of no more than a minute or so, I've been able to do the analysis. In terms of the output, you can see in the window at the bottom, it says adequacy factor on applied load is 3.852. What that means is that there's a multiplier on that unit pressure loading that I specified. The multiplier is 3.852, so I actually need 3.852 units to kilonewtons per meter squared to actually cause collapse. Okay, so that's sort of a quick look at how the software's been how the method's been implemented. Let's have a quick look at how we went about automating the method. And first to say that people have been trying to automate the method for for several decades now. So for example, I've got a couple of images on the next slide that are taken from an academic paper published in the early 70s. A guy called Henry Chan, working at the University of Oxford at the time, proposed that one could use rigid finite elements with potential yield lines at the edges of those rigid finite elements and use optimization to find the critical subset at collapse. The big issue, however, was that the topology of the mesh influenced the results that would be obtained. So for example, in order to identify fan-type mechanisms, then you would need to have a mesh, which a sort of radially oriented mesh. Some work was done subsequent to this point to try to improve the mechanisms that were obtained, but given how imprecise the mechanisms were, didn't really do the job. So really, this use of this element-based approach proved to be not the right way of automating the method. If we think about identifying fans, which is something that the rigid finite element method couldn't do, then we can see that there are other methods in the literature which can successfully identify fans. So if we move to a completely different field now, if we move to a field of truss design and look at a method called truss layout optimization, we'll see that actually we can use this method to identify fan-type geometries. If you're not familiar with truss layout optimization, now I'll just briefly talk you through how it works. What you do is you specify support conditions, a design domain, and an applied load. You populate that design domain with potential nodes, and you can have a moderate number of nodes, as we've got in the second image, or you can have very few nodes, as we have in the third image. And what we do is we connect those nodes together, and then we use optimization to find the most optimal layout of, in this case, truss bars. And normally with truss layout optimization, what we're trying to do is minimize the volume of the truss. So we're finding the topology or the layout that corresponds to that objective. So here we've put in very few nodes. If we put in more nodes, then we can get more complex truss topologies, and you can actually see here that we get a fan-type geometry. If we change the formulation slightly, so instead of dealing with supports and externally applied loads, we actually think of a self-stress or pre-stress problem, then we can actually get the full fan-type geometry that, if we're approaching this from a slab perspective, corresponds to the point load on a slab problem. So we felt it was worth looking at the mathematics underpinning the truss layout optimization method and see how that could be modified to deal with the analysis of slabs. So what we're trying to do in the classical truss problem is minimize the volume, which is the sum of the length times the area of all the truss bars. If we have problem variables of bar forces, then we can rearrange that so the volume is the sum of the length of the yield stress times the bar force. In terms of constraints, the constraints that are involved in that formulation are nodal equilibrium constraints. So what we're simply doing is every node we're making sure that we have equilibrium in the x direction and in the y direction. I mentioned that the self-stress formulation was actually slightly more akin to the slab problem. This is something that was actually pointed out by Denton back in, I think, around 2000. So if we look at the formulation for trusses, it's slightly changed. The main difference is when we look at nodal equilibrium, at the right-hand side, we don't have any externally applied loads, but instead we have an additional constraint which applies the self-stress. Problem variables remain the same, bar forces. For the slab problem, what we find is that a mathematically equivalent formulation involves, instead of bar forces, actually rotations at yield lines, and instead of nodal equilibrium, nodal compatibility. So we're actually looking at a mathematically equivalent formulation which isn't an equilibrium formulation, it's actually a work formulation involving compatibility. Instead of minimizing volume, we're minimizing energy. Instead of applying self-stress, we're applying a unit displacement according to the principle of virtual work. But mathematically speaking, these are equivalent, and mathematically speaking, these are very, very simple to solve. We can solve these using very widely available linear optimization problems. And from an end user's perspective, that means that we can solve problems very, very quickly. So just have a quick look at one of the key constraints that's present in the slab formulation. We said that instead of considering equilibrium at nodes, we're considering compatibility. What does that actually mean? Well, if we zoom in on a node that's, for example, got 1, 2, 3, 4, 5 yield lines converging on it, then what we're doing is we're resolving the rotations in the x direction and in the y direction and ensuring they sum up to 0. What it actually means is that if we sit at some point in the slab and we actually go round the outside of a node, when we get back to the starting point, the rotation of the slab must be the same as it was to start with. And it must be the same in terms of x rotation and y rotation. The big thing to note is that we explicitly enforce compatibility at nodes, but the formulation leads to many crossover points, and at those crossover points, for example, the one shown at the center of the slab in the bottom image, there is no explicit node, and so explicitly compatibility is not enforced there. But what we find is, according to the formulation, compatibility is actually implicitly enforced at all the crossover points. So the outcomes that we get are compatible at all locations. Okay, so let's look at some examples. First example we looked at is quite an academic one. It's a fixed square slab. Actually, what we're doing here is looking at 1/8 of it. The analytical solution was found in the 70s to be 42.851. We found a very close numerical solution, 42.857. So identical in all but the last significant figure. And what we actually did was we ran this problem with more and more nodes, and we found that if you extrapolate the solution to infinity, then we find that the solution that we get is the same to all 5 significant figures as that's shown in the literature. So this gives us confidence that the approach that we've developed is actually giving correct results, which is clearly important. Slightly more practical problem next. We've got an indented slab with both fixed and simple supports. We've got a number of literature solutions for this problem. Most recently, probably the solution obtained by Jackson, where the load factor obtained was 29.2. We actually identified a better solution, improved solution, albeit one which is more geometrically complex, as you can see. And to address the latter, one of the things that we have explored is methods of simplifying the mechanism that's identified. So the solution obtained in A is actually better than the solution shown, for example, in C, D, E, and F. But if you were doing a hand calculation to check the solution, then you'd far rather check the solution shown in F than you would the solution in A. So this is something that we're considering including in a forthcoming version of LimitState SLAB, although we haven't yet. We'll find out whether this is something that customers would find useful or not. Okay, so the last example that I'm going to show you is a slab in an apartment block. The particular apartment block was looked at in the Kennedy and Goodchild 2004 guide, and what they proposed is that a large number of potential failure mechanisms or yield line patterns were checked, and the most critical of one of those clearly used in the design. Clearly, with a complex geometry like this, it's quite a long process to do the hand analysis, and also because of the likelihood that you're going to miss the true critical mechanism, Kennedy and Goodchild proposed that you apply a margin of safety of 15%, which is relatively large number to include in the in the design process. So with the software, we entered the geometry and very quickly could identify the critical yield line pattern. So the software will home in straight away on the critical yield line pattern. There's no need to consider many alternatives. It will go straight there, and you can see here at the right hand side we're animating that to aid understanding of the mode of response. Okay, so just to wrap up with some conclusions. Yield line method is a powerful method. It's long been known to be a powerful method. The main problem in recent years has been the lack of a computer-based implementation. We've automated it using what's termed the discontinuity optimization method, which, as you've seen, is in a sense an extension of the truss layout optimization method. The key features of that is it involves linear optimization, so it's quick to get solutions, and it's quick to get solutions of whatever type. So that can be fan type mechanisms, arbitrary mechanisms can be identified automatically. And then obviously the last thing to say is software incorporating the method is now available, which is what my colleague Tom Pritchard will talk to you about a little bit more now. Okay, just hand you over to Tom.
Thanks, Matthew. I should now take you through the software interface and then a little bit more about the sort of wizards and the general usage in LimitState SLAB, finishing off with a few examples of sort of arbitrary and complex geometries. So if we open up the software, what we can see is, and we may as well leave Matthew's example still on there, is that we've got the viewer window in the center there that actually all of the visualization is done, and then it's a usual sort of software interface with the menu system up at the top, and then the toolbars down at the bottom, the output window where you'll find what the adequacy factor is, and also the software report if there are any issues with the model or anything like that, then you'll see that in the output window, and also you can flick onto different tabs to describe the boundaries and the loading. And then the two things that are potentially the most useful parts of the interface are the slab definition explorer on the left hand side here, which is where you will see listed all of the different slab definitions, which are essentially material properties that are available to apply to the problem. And then on the right hand side is the property editor, so anything that you actually click on within the viewer window or even one of the slab definitions, the property editor will then show the properties for that particular object. So in this case it's the solid that defines the slab, and we can see here what the spacing of the nodes is for when you do actually come to solve the problem, and also what the slab definition that's applied to it is. In this case it's the unit MP weightless slab definition. So that's a little bit about the interface. If we'll just jump in sort of quickly into the wizards and the general usage of the software itself. So if I click this button up here for a new problem, what we can see is it creates a new project, and we've got a couple of wizards just to very quickly be able to generate quite a standard problem. For both of these here is the rectangular slab, either with or without a hole. And what that does, it allows you to very quickly set up a rectangular slab problem, but then at the same time you can come out of it afterwards and make alterations to it as you see fit. So that's precisely what we're going to do here. So I'll choose a rectangular slab problem, and you'll see that it comes into this wizard dialog here. First off is the project settings, which are sort of pretty much the sort of general stuff, so project name, reference number, any comments, and also you can add tags to the problems down here, which then if you're using a Windows interface you can then search for when you're doing a general file search, and it will find the file for you. So it's just to aid finding the problem at a later date. We go on to the geometry, which is the sort of the meat of the problem. You can see here that there's an image just explaining exactly what's going on, and in this case it's just a standard rectangular slab. You can also apply a skew to it should you see fit, which is this alpha value down here, but also just input the width and the height. We're going to leave the default values of a width of 5 meters and a height of 4 meters, but then on the right hand side here we can change the support types as well for each of the different boundaries, and what I'm going to do is just set all of them to be simple. So we've set the geometry. The next thing that we're interested in is the materials that are actually used within the problem, or as we call them slab definitions. We've got existing ones here, so we can use the unit MP weightless properties that Matthew had used in his previous example, and there's also things like zero strength concrete and also unit MP concrete. So that's basically got unit MP but also with a sort of a realistic self-weight as well. But what I'm going to do is just create a new slab definition, and I'll call it slab 1. Apply a colour of some description, so I'll make it white grey. And then in the properties you can see that we have 2 directions of MP that we can apply MP values for. So it's basically in sort of, normal to the direction of the rebar, so the angle that you put in there. So say 0 is actually looking at vertical rebar, and 90 degrees is looking at horizontal rebar, and you put in the positive and the negative, so the hogging and the sagging MP values there. So I'm going to leave them as 1 in all directions. So we've got an isotropic slab properties, and also you can set the thickness and the unit weight of the slab definition underneath there, and that means that what you can do is then apply different zones to have different thicknesses of slab in that area. So you can do like drop panels and things around columns. But we're just going to leave them all as being the defaults for the moment. So the next thing we want to do is we've got a geometry, we've got the slab definition applied to it, we want to look at what the loads are, and for our problems here we can apply either self-weight loads, pressure loads, line loads or point loads, and we can either use ones that are built in, so we've got unit pressure, and similarly unit line is available if we wanted to use that, or unit points that are built into the software, or you can also define your own types of load, which we'll look at briefly later on. As far as the action type goes, if we've got a unit pressure load on it, which we're going to have in this case, then that will be generally regarded as being unfavourable, but if you wanted to change that to either neutral or favourable, so then it would use a different partial factor set when it comes to the analysis, then you can do that there. We're setting the adequacy as true, so that's basically saying that we want to multiply up this unit pressure load as part of the solution process and work out what the multiplier on that load is that would cause collapse. And then lastly, we've got the position, which in this case is just saying S1, which is, if I click on change, you can see S1 is just the entire solid. So we'll use that. And then lastly, we come on to the analysis tab, which in this case is just basically setting the nodal density. So if you remember when Matthew was explaining previously that the number of nodes that you put into the problem will affect the accuracy of the solution. So obviously if you have a very low number of loads, then the solution won't be quite as accurate, but the time of solve will be a lot quicker. But then if you want to get within sort of 0.1% of an answer, then you put a higher number of nodes in, and you will get increasingly more accurate results. So, but in our case, what we're going to do is just leave it on a medium, which is a target number of 500 nodes for the entire problem, and click Finish. This is just showing some quick tips for new users of the software just to get them going, so we'll just OK that. And if I click the Solve button, what you can see is it's going through the potential failure mechanisms until it comes to the one which is actually critical, and it's animated it quite quickly, so I'll just flick it back to the original, which is showing you there that you've got the classical envelope type arrangement of yield lines, and as we saw, if you click the animate button, you can then displace it to see in better detail how the problem is actually behaving at the point of failure. And you can also put it on rotate and spin the model around. I mean, it's not particularly interesting in this case, but you can see what's going on here. And then of interest to a lot of people is actually having a report that they can then print out and show to clients or to colleagues and things. So we can do that in this case. So you go to the report and the options, just the different sections in it. So about the method and the summary. So it should tell you what the adequacy factor and the critical failure mechanism is. And then bits about the geometry, the materials, the partial factors and the load cases that are applied. And you can see here that it puts it all out in sort of a tabular form. Right at the top it will tell you what the critical load case is, what the adequacy factor is, give you an image of the failure mechanism, and then go through all the different details. And obviously if you've got more load cases or if you've got a more complex structure, then the more detail that will be in there. So we've done that. We've got an adequacy factor of 1.22. We've got this sort of quite simple envelope-shaped failure mechanism. One of the beauties of the software is that you can very quickly make changes to it. As I sort of alluded to earlier, the wizard is seen as sort of a quick entry into having a model that you can then play with later and sort of adapt to your needs. So if I just unlock this, go back to the basic rectangle, one of the things that we might want to do is use an orthotropic slab definition rather than an isotropic one like we've been using originally. So all we need to do to change that is go to the slab definition explorer on the left here, click on slab 1, which is the definition that's used within our problem, and then in the property editor we can see that all the different properties of that slab definition are then presented to us. And if we wanted to change it, say for example I wanted the rebar in one direction to have a higher strength, so I'll just put 5 in for the sake of it, then we can do that. And then if I solve again, what we'll see is that actually we get the envelope failure mechanism again, but what's happening in this case is this horizontal section in the middle here is expanded out, so the sort of triangles at the ends are smaller, so obviously that change has had an effect on the problem. And also you can see that the solution now has gone up pretty much threefold from being 1.22 to being 3.77. So the adequacy factor associated with this failure mechanism is telling us that the load needs to be much higher because we've got a higher strength slab in there. So that's just one of the changes we can make, and what I'm going to do is actually just change it back to being an isotropic slab. Something else we might want to do is potentially see what effect having a column in the centre of it is. So if I put the grid on, what we can do very quickly is just draw a rectangle and provide supports to the edges of that rectangle, and that will effectively simulate the presence of a column. So what I'm going to do is add a point, and I think we'll go from 2.2. Ooh, excuse me, that was wrong. We want to go from 2.2, 1.9 to 2.4, 2.1. So adding a small square in there, you can see that adding it in the centre of the slab has actually included also these additional boundary lines to actually connect that to the external boundaries of the problem. So that's one of the things that you need to do within the software, is to just make sure that the different zones are all connected. So what I do is select that column in the centre and just delete it, so that now there's no material in the centre there. Select all the edge boundaries, and you can see in the property editor there we can then differentiate between the different things we've selected. So I want just the external boundaries, and if I set the supports to say they're fixed, then we've basically got a column in the centre of the slab there, and we can solve and see what the effect of having that there is. And we can see within a matter of seconds we've seen what the critical failure mechanism is. Actually, I'll just take it back, and it's quite a nice sort of wheel mechanism around the column, and then sort of a pseudo envelope around that, and we can animate it as we've done previously, and also rotate the problem itself just to inspect what the critical failure mechanism is like once it's actually animated, and it gives you a good insight into how the slab behaves under the critical loading. So in this case you can see that around the column there the failure mechanism is sort of giving you this wheel. So we've done that, we've added a column to it. We've seen here that the adequacy factor is just over double what we had originally, so it's gone from 1.22 to about 2.86. Another thing we might want to do in this case, if I unlock it, is change the boundary conditions around the edges of the slab. So what we can do is to select maybe the right hand side, and on the external boundaries, instead of them being simple supported, let's make them free, so that that's an entirely free edge. We've got this column still in the middle. If we solve again, we can see that the mechanism has now changed quite dramatically from being a sort of combination of the wheel and the envelope shape to actually just being a failure involving the free edge and the space between the free edge and the column. And we can animate that just to see exactly how that's acting. And in this case the adequacy factor is actually still slightly higher than it was originally, so we've gone from 1.22 to 1.51. And then lastly, for this particular thing, perhaps we might want to add another column. Say if we've got that free edge and we didn't want that failure mechanism, we want to make it slightly stronger, we could potentially just add another column on the right hand side there in exactly the same way as we did before. So just draw the rectangle, delete the middle of it, make the edges fixed, and then when we come to solve this one, we can see we're going back to the sort of wheel mechanism in combination with the envelope, but the adequacy factor has increased from sort of 1.22 without any columns to 1.5 when we just had the free edge and the single column, and now that's nearly doubled to 2.88 when we've added this extra column on the right hand side just to add extra support in the centre of the part that was failing previously. So that's given you a very quick flavour of how you can set up a problem using one of the wizards and then modify it to your needs, just to sort of see what the effects of various different changes are. Another way that you can actually generate a problem in LimitState SLAB is to just start from scratch and define your own problem without the use of the wizard. So we can do that now. So in the quick create part here, instead of going for one of the wizards, we're just going to start with an empty slab, and as before we had the project settings, and then also there is the grid settings, which is the part that you can set sort of the snap properties and also the intervals of the grid. So if you've got something that you want to make quite sort of fine-grained changes to, then you can have a smaller grid and snap to that, or if you don't really mind, you can have quite a large grid and just work with it as that is. So what we'll do, if I just click finish, you can see we've got standard grid with sort of 10 centimeter spacings on the minor grid points. So we've got nothing there at the moment, so basically we need to go through the process of defining a geometry, adding load to it, adding support to it, and then finally a material, and then solving. So if we start off by creating the geometry, and what I want to do just for fun is I'm going to make sort of a cruciform shaped slab. So I've drawn that there. That was quite easy, and obviously what I said, the next step is to provide some support. So if we select the entire structure using the rectangle select, again in the property editor, just go select the external boundaries out of those and then change the support type to be simple, and you can see the simple support has been applied to all of those external boundaries there. So we've got the geometry, we've got the supports. The next thing that we need is a material, or a slab definition as we call it. What we need to do, if I right click in the slab definition explorer, we can create a new one, and I'm going to call it slab 2, give it a colour, we'll make it just a light green colour just to be different, and what we do, if we just keep the properties to be isotropic as it is to start with, and then all I need to do to apply that to the slab is either to drag and drop it on, you can see there, or alternatively, and this is quite useful if you've got a lot of different solid zones within quite a complex geometry, is you can actually select one or more in the viewer. In this case we've only got the one, and you can see in the property editor that we have a slab definition field. If I click in there and click change, we can use slab 2 within that region by doing that. So if I had like 5 or 6 different regions selected, then probably the easiest way of actually applying the same slab definition to each of them is to use the property editor rather than the drag and drop functionality. But anyway, we've got this slab property applied to it, we've got the geometry, the support conditions. The last thing we need is some loading. So what we need to do there is we can use these purple buttons at the top here. The left hand one actually opens the load case manager dialog, which we'll go into shortly, and then the next 3 will apply a point, a line, or a pressure load to a selected area. So in this case we want a pressure load, so I'll select that. Dialog opens up asking me to select the solids that I want to apply a pressure load to, so I'm going to select that one, click OK, and then the next dialog just says what type of pressure load do you want to apply to it. So we've already got one, as discussed previously, which is the unit pressure, which is an existing load, or we could create our own if we wanted to. So if we click OK, we've now got unit pressure load and a cross, so we've got all the different aspects of the problem that we need to actually look at. So I can click solve, and what happens is we get quite a nice failure mechanism with an aggregate factor on the applied loading of 11.73. But again, what if we wanted to change something? If we bring up the grid, it's very easy to do that. So you say I wanted to actually make the slab a bit larger. What we can do is just grab things and move them very, very easily. So I'm just making the arms of this cross larger than they were previously. We can solve again, see what the failure mechanism is like, and in this case we've got this sort of rose petal type failure mechanisms spreading out from the corners in each case. So you can see there that you can very quickly sort of create and modify again a problem from scratch using the software. The last way, so I want to very quickly just explain how you can get a problem into the software, is actually using a DXF file. So perhaps you've got a drawing of a problem that you've been provided with. You can very easily use that to create a geometry and then import that into the software in order to create what would be a more complex problem. So if I just go to File, Import Geometry, what I'm going to do is look at an apartment block floor slab that I've already set up in a DXF file. It's asking which layers I want to import. If I open that, you can see here that just using the lines in the DXF, it will create a problem for you. So as long as you've got closed loops within your DXF file, it will then convert those to solids within the software and allow you to then use that as the basis for a model. So obviously you can create the materials and drag them and drop them, or assign them using the property editor as we discussed previously. We don't really have time to go through the whole process of doing that at the moment, so what I'll do is I'll just open the problem as we've made it, and this is available within the example files of the software when you install it. So we've got all the different types of area where we're applying different materials and different loading to it, and you can solve it, and you can see that the software is very quickly homes in on the critical collapse mechanism for this particular problem. So I think time is running out, so what we'll do now is have a look and see if we have any questions from people. So if you have any, then do please feel free to use the question functionality that's within the software, and we will try and answer them for you. What I'll do is I'll just pass you back over to Matthew to answer some of those as they come in.
Thanks, Tom. Okay, so if you have any questions, please fire away. Just while I'm waiting for some questions, just a couple of questions that have come up in the past. So one question has been, can slab depth be varied linearly across its span stroke width? The answer is not directly. However, what you can do is you can prescribe or define a series of zones, each with different properties, in order to have a sort of a piecewise representation of a slab that varies linearly. In the future, we may add this functionality. Could it be used? So I've got a question coming in. Could it be used for bridge deck slabs with a HP vehicle superimposed over several positions? I don't think we showed a bridge example. Tom, do you want to just load up a bridge example so we can give this delegate an indication? So we're just loading up something. So we've got quite a number of load cases, so and so actually Tom has changed to very coarse, so we've got a very, very crude representation of a vehicle moving across. The loads are not actually you can see now that the loads moving across. The answer is that you can define vehicles, you can move them across the bridge, and you can identify which is the critical failure mechanism. We've done this on a very coarse resolution, and you can see at the end the most critical mechanism is identified, and critical load factor. In this particular case, we've not got realistic vehicle wheel loads, so we've actually got a very large adequacy factor of 20.8. But hopefully that gives you a sense of what you can do. Any other questions before we close? No, I think that's probably it. I'll hand you back to Tom, who will just wrap up the proceedings. Thanks.
Thanks, Matthew, and thanks everyone for attending. We hope you found it informative, and as mentioned at the start, if the presentation has raised any questions that we haven't actually answered in this last section, then please do get in touch via telephone or info@limitstate.com, and we'll be more than happy to speak to you about it. LimitState SLAB, as Matthew said, is available to download or purchase now from our website, so if you go to www.limitstate.com. We'll also be in touch over the next few days just to get some feedback on the webinar and to find out if you have any further questions or whether you think that LimitState SLAB might actually be useful to you. If you'd like to watch the webinar again or think you might know somebody who would be interested to see it, there'll be a recording available later on, and you'll receive an email with a link to it once it's available online. Also, please do look out for our other webinars that deal with both LimitState SLAB and its sister products, so LimitState Ring and LimitState Geo. We'll be sending out event notifications in advance of these, but they're also posted on our website at limitstate.com/webinars. Finally, I'd like to say thank you to everybody for listening. I hope you can join us again for one of the future sessions. We'll see you then. Thank you.